All right, so we are taking a look at section 13.3, day 1. We're going to be looking at arc length, which is something you looked at a little bit in Calc 2 for plane curves, and we're going to extend our knowledge of that now to space curves in 3D. Okay. So last year you looked at, for a plane curve, let's say we have a vector valued function given by f of ti plus g of tj. So in other words, x is given parametrically by some function f of t, and y is given parametrically by some function g of t. On the interval from a to b is our range for the parameter value t. Then the length of that plane curve, the arc length, if I wanted to know how long that curve was from t equals a to t equals b, I would take the integral of the square root of dx dt squared plus dy dt squared, or in other words, the square root of f prime of t squared plus g prime of t squared. And in application problems last year, aka when you were doing PVA, position velocity acceleration, this would have been a way to find the total, my pen is acting up, the total distance traveled. Right, that integrand would have been an expression for the speed. So this would have been the total distance traveled between time t equals a and t equals b. So looking at the time interval from a to b. Okay. And we define a 3D space curve's arc length in exactly the same way. The only difference is now, instead of just having an x and y component, now we also have a z component. So we're allowing the z component to be given by this real valued function h of t. We're still looking at a parameter value from a to b. Assuming that the derivatives are continuous, then the length of that curve is going to look exactly the same with a third component now. We're going to take the integral from a to b. We're going to take the square root of f prime of t squared plus g prime of t squared plus h prime of t squared, or written in differential notation, dx dt squared plus dy dt squared plus dz dt squared. And remember from last year, this is really just what we're doing is we're approximating the length of this curve using these little polygonal paths. Okay, we're taking the limit of the lengths of those polygonal paths, and it ends up, the more of those little polygons that we put together, it gives us a way to find the length of this space curve here. Okay, so this would be from, t equals a to t equals b, and we're assuming that we traverse that path exactly once so that we're not overcompensating for that length. You can write this in a more compact way using vector notation. So one way you'll see often this year that we express the arc length of a space curve is it's the integral from a to b of the magnitude of the tangent vector r prime of t. Now, why does that work? This one is worth not really proving, but just showing you why this works. We were given that the position function was given by f of t, g of t, h of t. So let's try to work our way and justify why this works here. Well, we need the magnitude of r prime before we take the magnitude. So what would the tangent vector would be given by the derivatives of each of the components, f prime of t, g prime of t, and h prime of t. And then to take the magnitude of that tangent vector, we take the square root of the sums of the squares of the components. Well, that would just be the square root of f prime of t squared plus g prime of t squared plus h prime of t squared. But that's exactly what we had here. So it's just a more compact way of writing it. So these are equivalent. Oftentimes you'll see the vector notation expressed instead. Okay, so let's take a look at an example here. I can scroll down. Let's see. There we go. Example 1. Find the arc length of the circular helix r of t equals 3 cosine t, 3 sine t, 4t, from the point 3, 0, 0 to the point negative 3, 0, 4 pi. So remember, our circular helix was that slinky type spiral pattern. We want to find the length from the point 3, 0, 0 to the point negative 3, 0, 4 pi. First thing we need to do is figure out what our parameter values are going to be. What's the domain of our parameter? In order to get to the point 3, 0, 0, we would need t to equal 0. In order to get to the point -3, 0, 4 pi, looking at that k component, if 4t needs to equal 4 pi, then I know t has to equal pi. So I know that I'm integrating from 0 to pi. Okay. I also know that I'm going to be needing, if I'm going to write my little formula off to the side, I need the arc length to be the integral from a to b of the magnitude of r prime of t. Oftentimes I see students take the magnitude of r of t. That's not correct because we need to integrate speed in order to get total distance. We don't want to integrate position. So I need to take the derivative vector. Derivative of 3 cosine t would be -3 sine t. The derivative of 3 sine t would be 3 cosine t. And the derivative of 4t would be 4. So then the magnitude of r prime, I like to do my computations off to the side before I do the integral. This would be the square root of the sums of squares of the components of r prime. So if I take the sums of squares of components here, 4 squared would be 16. Let's see what we get. We end up getting, we're going to get a sine squared plus cosine squared, right? So we're going to get 9 times sine squared t plus cosine squared t, but that's just equal to 1. That's one of those good old Pythagorean identities that we like quite a bit. So this just ends up giving me the square root of 9. This part's equal to 1 plus 16, which would be the square root of 25, which is 5. So to get the arc length, I'm taking the integral from 0 to pi of the magnitude of r prime of t, which we just calculated to be 5. Okay. So we end up getting, this would be 5t evaluated from 0 to pi would be 5 pi. So that's the length, maybe one of the points, I don't know if this is exactly where they're at on the curve, but maybe it starts here and ends here. What we just found is the length of the path from t equals 0 to t equals pi. That length of that blue piece ends up being 5 pi. Okay. Just to give you an idea. Okay. What's nice about this, so we have different ways we can parameterize the same curve. So if, take this helix that I have up here. This isn't the only way to parameterize the curve. I can redefine t in a different way and still get the exact same shape. So as a real basic example, we have a famous space curve called the twisted cubic, given by r1 of t. So this is parameterization number 1. The x component is t, the y component is t squared, and the z component is t cubed. So every component ends up increasing the power of the exponent by 1. And we're just looking at the portion from t equals 1 to t equals 2. However, we could redefine t in a different way. So we could introduce a new parameter. Let's say that we let t equal e to the u. Well, then I'm going to end up getting a second parameterization for that curve. The x component would become e to the u. The y component would become e to the u squared, or e to the 2u. And the z component would become e to the u all raised to the power of 3, which is e to the 3u. Now, by redefining the components in terms of this new variable u, this new parameter, the bounds on that parameter are going to have to change. T went from 1 to 2. But now, since I defined t to be e to the u, that means that u is going to have to range from 0 to the natural log of 2. And I'm just getting that by kind of solving, e to the u equals 0. Well, that would imply that, e to the u equals 1 would imply that u has to be 0, and e to the u equals 2. These are my t values over here. Would imply that if I take the natural log of both sides, u has to be natural log 2. So these would be my new bounds on my parameter. They look like different parameterizations. They are, but they define the same curve. And that's the idea, is you can have multiple parameterizations defining the same curve. I did a quick sketch of these in CalcPlot 3D. And you'll notice that it looks like one curve that I have here. Here's your twisted cubic. You could zoom out a little bit if you want to see it a little bit more. But I actually have both of these parameterizations sketched on the same screen. So the one I have at the top is the second one, and the one I have on the bottom is the first one. This one's R1, and this one's R2, but notice there's only one space curve showing up because it's the same curve. So just different ways to look at the same curve. So that should make you think, okay, what if we calculated the arc length using those two parameterizations? Would we get the same length or would we get different lengths? So use your intuition to make a prediction, and we're going to check it here by setting up the integral expressions for each parameterization. So let's say I wanted to use the first parameterization, R1. Okay. Then I'm going to need the derivative vector, first of all. So R1 prime of t would be 1, 2t, 3t squared. And so then to find the arc length, I'm going to integrate. Our t values range from 1 to 2 for the first parameterization. Square root of the sums of squares of the components of R1 prime. So that'll be 1 plus 4t squared plus 9t to the fourth. Definitely, we're going to use a calculator for that one. That is not easy to integrate by hand. If you remember, you can use Math 9 on your TI-84 in order to compute that integral. So if you do that, maybe this one I'll show you. Math 9, we're going to go from 1 to 2 of the square root of 1 plus 4. I'm going to use x on the calculator. Doesn't matter what variable I use. Plus 9x to the power of 4. Make sure that you specify the variable that you are differentiating with respect to. So we get about 7.7075. Okay, so that's the arc length of the first parameterization of that twisted cubic. Now, using the same curve, let's see what happens if we find the arc length using parameterization number 2. So R2 prime, here's R2 up here, would be e to the u. Actually, I should call this R2 prime of u, not t. So let's do u, my bad. So I get e to the u. Using the chain rule, I get 2e to the 2u, and I get 3e to the 3u. And let's see what I get. So now, taking the length. Now remember, now the bounds aren't going from 1 to 2. What were our bounds for the second parameterization? 0 to natural log 2. 0 to natural log 2. Square root, sums of the squares of these components that I'm highlighting would be e to the 2u plus 4e to the 4u plus 9e to the 6u. Okay. du. Oh, I forgot my dt up top. Major error, sorry. This one should be du. Make sure that you put your differential inside your integral. And spoiler alert, probably not surprising, you actually get the same result. You can check that using Math 9 on your calculator on your own if you'd like. So big takeaway from this is the arc length is independent of the parameterization. That's a very, very important message. Arc length is independent of the parameterization. And so you'll see in a little bit, it's going to be helpful to re-parameterize some of these functions with respect to arc length, since it doesn't matter what parameterization we use. Hence, we have what's called the arc length function, which is given by the letter s. Okay, so let's say we have some space curve given by the same components we've been working with this whole section. Functions f of t, g of t, and h of t define x, y, and z respectively. T ranges from a to b. We're assuming that these functions f, g, and h have continuous derivatives, so r prime is continuous, and we're assuming that c is traversed exactly once as t ranges from a to b. Then we end up getting this accumulation function, which is called the arc length function, s of t. And we denote it by s. And what it is it looks very similar to the integral we just looked at on the last 2 pages. We're integrating the magnitude of r prime. One thing you'll notice, though, is I'm not specifying a fixed upper bound. I'm just letting it be the general parameter t. Okay, so it doesn't have a fixed stopping point. And for that reason, if you remember from last year, if there's a variable as one of your bounds of integration, then you can't have the same variable in the integrand, which is why you see a u in the integrand, but you see a t as the upper bound. So a is going to be your starting point, your starting value of t. But we just want a general function no matter where we stop, whether we stop at 10 or whether we stop at t equals 12 or whether we stop at t equals 15. We want a function so that we don't have to integrate every single time. So the integrand doesn't change. But now it's an accumulation function that has an upper bound of t. Okay? So S of t is just the length of the part of the curve between r of a, this is where you want to start, and the general expression r of t, which is where you want to stop. So visually, that would be the length of this pink part right here if I connect those two position vectors. Okay. Differentiating both sides, if I take the derivative of that accumulation function, something you guys did last year, the fundamental theorem of calculus says that I can plug that upper bound of t in for u. So ds dt would be the magnitude of r prime of t. Depending on what textbook you use, that could either be part 1 or part 2 of the fundamental theorem of calculus. And in application problems that you studied last year, this was speed. It's the magnitude of that velocity vector. Oftentimes, we'll multiply the dt to the other side. We want to take integrals with respect to arc length. So just looking at that arc length component, ds, this is the arc length component, we can multiply dt to the other side, and we end up getting that ds is equal to the magnitude of r prime of t times dt. Okay. And so we'll be parameterizing curves with respect to arc length. The reason we want to do that is because it doesn't depend on any coordinate system. We're going to look at a lot of different coordinate systems this year as we move into second semester. But for now, more importantly, if you parameterize a curve with respect to arc length is independent of parameterization. So just like we saw on the last page, it didn't matter whether we expressed this twisted cubic using R1 or R2, because when we calculated the arc length, we ended up getting the exact same length. Okay? And oftentimes, depending on the parameterization that you pick, you might be able to calculate an easier integral. I probably wouldn't have called either of these two integrals easy to do. But if you can find a parameterization that's easy to integrate by hand, arc length is independent of parameterization. So there are benefits. And so really all we do is we re-express t in terms of this arc length function s. So we try to find an expression for the parameter t in terms of s, this function t of s. And then we can just re-parameterize the curve by substituting in s there. Okay. So for example, if s was equal to 3, then r of t of 3 would be the position vector of the point 3 units of length along the curve from the starting point. Okay? Because s equals 3 would indicate a length of 3. So this would tell me how far a particle moved 3 units along the curve. Okay, so let's try one. Let's re-parameterize our helix. We keep going back to this example of the helix. R of t equals cosine t, sine t, t. I'm going to write it in component form because I like that better. Cosine t, sine t, t. I want to re-parameterize that helix with respect to arc length, s, measured from 1, 0, 0 in the direction of increasing t, so in the direction of increasing parameter. First thing I'm going to do is just figure out what value of t would indicate the point 1, 0, 0. Just using a little bit of deduction here, if cosine t equals 1, sine t equals 0, and t equals 0, well then the z component gives it away. It means we're starting at t equals 0. It does not tell us where to stop, so that means that we're going to be going until general t. We're not stopping at t equals 5 or t equals pi. We're just going to create this arc length function, s of t. So step 1, I'm going to define the arc length function is going to go from t equals 0, where we start, to general t of the magnitude of r prime of u. I need a different variable, du. So off to the side, I'm going to do my side work here. I need to figure out what r prime of u would be. Well, r of u would just be the same parameterization they gave me using u instead of t. So r prime of u, and you could do all this work inside the integral if you want. I just like to do it off to the side. So I'm going to call this side work. Up to you, just stay organized. This would be negative sine of u, cosine of u, 1. So then magnitude r prime of u would be the square root of negative sine squared u would be sine squared u. Cosine u squared would be cosine squared u. 1 squared would be 1. We would end up getting, there we go again, Pythagorean identity, sine squared plus cosine squared is equal to 1. Square root of 1 plus 1 would be square root of 2. So we end up getting the integral from 0 to t of the square root of 2 du. So we end up getting t squared of 2. So what does this tell me? Re-parametrizing, now what I know, this implies that s is equal to t square root of 2. I want to express everything in terms of s, so I'm going to solve for t in terms of s. This would imply that t is equal to s over the square root of 2. Okay. That's what we need to get to. We need an expression for t in terms of s. This is my function t of s. So now all I'm going to do when I re-parameterize, therefore, r of t is a function of s. We're expressing this in terms of arc length. Would be, the first component was cosine t. Well, now it's going to be cosine of s over square root of 2 I. Plus, the second component was sine. So this would now be sine of s over square root of 2 j. And the third component was t, which is s over square root of 2. S over square root of 2 k. Now you might be thinking that looks overly complicated. Didn't the original one look easier? I would agree, it did, but now what's nice is if I said find the length of the helix from t equals 0 to t equals 5, you wouldn't have to go back and recalculate the integral because now you have a general expression where you can plug in different lengths of s. What if I said from t equals 0 to t equals 10? Now I can just plug in 10 for s. Or from t equals 0 to t equals 2 pi. I could plug in 2 pi for s. You don't have to go back and redo the integral every time. That's the benefit. So let's try it for one specific example. Find the point 5 units along the curve from t equals 0, from 1, 0, 0. This was t equals 0. 5 units along the curve means that the arc length is 5. So all I'm going to do is find r of t. I'm going to plug in 5 for s. So I end up getting, I'm going to do a vector first, then I'll change it to a point after. So the position vector, 5 units along the curve, plugging in 5 here for us, would be cosine of 5 over rad 2, sine of 5 over rad 2, and then 5 over rad 2. Okay. So then your point, they asked for a point, so let's just make sure that we give it as an ordered pair, would be cosine of 5 over rad 2, sine of 5 over rad 2, 5 over rad 2. As a decimal, again, typically you'd give things as an exact answer, but if I asked you to approximate, you can plug these in your calculator. This would be about negative 0.923, negative 0.384, and 3.536. Okay. So back to the visual from the last page, what would this indicate? This would be like our stopping point on this curve. This isn't the helix, but this is the idea, is that if this was t equals 0, now 5 units along the curve, if this length here was s equals 5, that stopping point would be the point we just found. Just so you can see visually what we did. Okay. And you could put these on CalcPlot 3D if you want to try it with the helix itself. Okay, last one. We have a space curve given by x of t equals natural log t, y of t equals 2t, and z of t equals t squared. Looking at the different things I'm going to have to do in this problem, I know at least by part C, I'm going to have to take an integral. In part A, they're asking me to find the magnitude of r prime of t. So first thing I'm going to do is find the derivative vector, the tangent vector r prime of t. The derivative of natural log t would be 1 over t. The derivative of 2t would be 2. And the derivative of t squared would be 2t. Taking the magnitude of r prime of t, I would get the square root of 1 over t squared plus 4 plus 4t squared. Now, you could leave it like that. By all means, that's a correct answer, but look at part C. You got to look ahead a little bit. You're going to have to integrate that function eventually. And it doesn't say use a calculator. So if I asked you right now, how do you integrate this function by hand? Ooh, that would be pretty messy. So there's got to be a way to simplify this so that you can use integration techniques that you're familiar with. There is no integration technique on that function currently that I see that would work. So popular technique, when something like this shows up under the radical, you would want it to be expressed as a perfect square so that you could apply that square root to that binomial. So that should give you a clue that this factors. And this is going to factor into 2t plus 1 over t quantity squared. That gets me my 4t squared. The middle term, the t in the numerator and the t in the denominator, will give me 4 with the outer and the inner term. And then the 1 over t at the end, when I square it, gives me 1 over t squared. Well, the square root of 2t plus 1 over t quantity squared, normally that would give me absolute value of 2t plus 1 over t, but I actually don't need the absolute value bars in this case, because if I look at the domain of the original space curve, natural log t is only defined for positive values of t. The second two components are defined for any real number, but remember, when we find the domain of a vector valued function, we need to find the intersection of the three individual domains. So the domain, I'm going to write it off to the side, of this vector valued function is only values t greater than 0. So I don't need the absolute value bars because I know that this quantity has to be greater than 0. And that'll help for part C. Part B, this is just more recognition. They're asking for the derivative of arc length with respect to time. If you remember from our last page, that is exactly the magnitude of r prime of t. That was when we took the derivative of that accumulation function of that arc length function. Well, then that's just going to be the exact same result that we just found in part A. 2t plus 1 over t. And part C, now we are finding the integral from 1 to 3 of r prime of t dt. So in other words, I'm finding the length of this space curve from t equals 1 to t equals 3. So I'm taking the integral from 1 to 3 of 2t plus 1 over t dt. Now you can see why I prefer this expression as opposed to what I had underneath the square root in part A. Much easier to integrate. The antiderivative of 2t would be t squared. The antiderivative of 1 over t would be natural log of absolute value t. Since we're integrating over positive values, you wouldn't technically need the absolute value here, but that is the antiderivative. And we're evaluating from 1 to 3. So we end up with, if we plug 3 in, we get 9 plus natural log 3, minus, if we plug 1 in, we get 1 plus natural log 1. So we end up with 9 plus natural log 3 minus natural log 1 is 0, minus 1. So we end up with a length along that curve of 8 plus natural log 3. Okay. It did not say use a calculator. If it said use a calculator, I would have just integrated this right over here and just plugged it in and done math 9 like I did before. But it did not. It wants an exact answer, so that's how we get around it. Okay, definitely go back, watch some parts of this again, especially the parts about re-parametrizing with respect to arc length. Some of the stuff at the beginning might seem like a review, but I think this part where we're re-parametrizing in terms of the variable s, might need to listen to it a couple times, and you'll definitely want to make sure you do the problems in the packet and your web assigned problems for some practice. There is a lot more to this section. Section 13.3 is the longest section in this chapter. So we'll make some future videos once we start talking about concepts like curvature, the unit normal vector, the binormal vector. We have a whole lot of fun stuff coming up in the rest of this section. So I'll make a couple more videos for that. For now, you can get started on your homework dealing with problems for arc length. Okay? All right, happy mathing. See you in the next video.